So, thank you all for being here. First, let me introduce myself. I'm Abhinav Vashisht. I'm a senior security researcher here at Appknox. My work mostly consists of pen testing mobile and web applications, uh, and I focus more on and I specialize in Android and iOS applications. In my free time, I also like to do some research, some independent security research, finding new vulnerabilities, maybe new attack vectors. Apart from this, I have also given a security talk in conferences like PH Days. And today, I'm going to be introducing all of you to reverse engineering. What is reverse engineering? Why do we need it? And what are some of the things we can do with reverse engineering during a regular VAPT? Questions, I will please feel free to ask me any questions. I will take questions at the end of each topic. So anything is not clear, feel free to jump in. So first question that we have is, what is reverse engineering? Deconstruction of any software to extract design information is what is called reverse engineering. Your ability to be able to extract any sort of useful information from a piece of software that would have otherwise not been available to you. That process is called reverse engineering, primarily done to analyze and understand how something works in the broader sense. What are some of the useful scenarios where reverse engineering could be useful? When you're working with closed source libraries, that means the source code is not available and you might run into some issues, maybe some errors. To help fix those or understand what went wrong, you can use reverse engineering. Some other scenarios like this can also be when the product has no active support. If you have an integrated product that is depreciated, but you still have to use it and things go wrong or you need to troubleshoot, reverse engineering can be your friend here as well. And lastly, if the documentation of a product is unavailable or not very clear, in that scenario also, this is something that can be really useful. Now we understood what it is and where it can be used, but you might have the question, why do I need it? What extra can I do when I'm able to reverse engineer? From a security industry standpoint, it is mainly used for identifying new vulnerabilities. Maybe there are closed source components that might give you new attack vectors when you reverse it and understand what is going on behind the scenes. But apart from cybersecurity, is there no other use for it? Of course not. Uh, if you are trying to explore or understand better a certain product or component that you are trying to use, you can use reverse engineering here. We can reconstruct outdated products, something like we can reconstruct outdated products to fit into newer times, to be able to fit them into newer times. We can use it there as well. Also, to improve existing design, when we understand the industry norm for a particular service or a product, when we are able to reverse it and understand what exactly is happening, we can also come up with better ideas on how we can improve it. So there is scope for improving system design as well. And lastly, inspiring creative minds with old ideas. Maybe you are not going to use the entire product or what you are going to reverse, or that might not be your main source or the main work that you're trying to do. But in the process of reverse engineering, I have found a lot of times you come across older implementations or design system designs that can be used in other places. So you can get creative with it and come up with crazier ideas as well. So these are some of the main reasons as to why you would need reverse engineering. So before we get started with the concept or performing reverse engineering, let us look at some keywords that we are going to come across for the remainder of this slide and what they mean. Sorry. Uh, so the first thing is assembly. Assembly is a mnemonic that translates machine level code. So when we write a C program or a Java, when we write a particular program, that code that we write is not what is executed by our systems or by our computers. It gets converted to binary data because that is what the processor understands, and that binary data is executed. Representing that binary data in human readable format is assembly. Primarily, this is done to understand when we are able to read assembly at the lower level, we are actually able to see what is actually happening when a particular software is executing, or we can understand better why something works or something doesn't work. So in the journey of reverse engineering, understanding assembly language is the first step. Familiarizing yourself with assembly language is the first step in reverse engineering. The second thing, the second term that we are going to come across is a compiler. Compiler is a piece of software that converts the high level code that we write into the binary data that I just explained, that it converts it into that executable format. That is the role of the compiler. It does that so we do not need to bother ourselves with writing the instructions to the processor or to a kernel. It converts our high level code to the machine code. The next topic that we are going to look at a lot are registers. Registers commonly are used by the processor to store memory during execution or after the execution of certain tasks at any time if the processor requires to store data. What this means is the arguments to a function maybe before it is being processed are stored in particular registers. When they are used in computation, the intermediary results are also stored in registers. And finally, the last result, the end result of the function, even that is stored in registers. So as you can see, registers are very versatile in nature. They can do a lot of different things, and they are very widely used by the processor. The next key topic that we're going to look at are instructions. Instructions, as the name suggests, are commands to the processor. Every software architecture or every software architecture comes with an instruction set, predefined instruction set on how to interact with the particular processor. So the binary data which is converted into assembly, we usually see the instructions and the registers that they use. That is typically what we are going to be looking at when we are reversing. And the last topic is binary file. A binary file, or binary for short, is the output of the compiler, which has a predetermined task which can be executed on any system of the same architecture. So if I compile a program on my Mac, for instance, I can share that with any other Mac user and they will be able to run the same program, given it is the same architecture. That is a binary file. So these 5 terms are going to be important moving forward. If there are any questions so far at this point, you can let me know. Okay. Okay, now that we have got some of the basic terms and we have got ourselves familiarized with some of those terms, how do we get started in reverse engineering? How can I get started today? So the first important thing that we need to understand is there are two different types of architectures. There is 32-bit and 64-bit. And the machine level code, the mnemonics, the representations are a little bit different in both of them because they are different architectures. Their internal the internal mnemonics are different. So before you start reversing, the first thing you need to see is it a 32-bit or a 64-bit? There are a lot of differences. We can see them as we go further down in the slides. I will not go through all of them here, but this is the broad categorization. The first thing that you need to check when you're reversing is to see if you're doing a 32-bit or a 64-bit executable. Now, let us understand, I briefly spoke about a binary file or a binary 2 slides ago. The binary can also be called an executable sometimes. They mean the same thing. So to get started with reverse engineering, let us see what are the components of this binary file. What all do they have, and what are each of these components going to be used for? The first one is the heap. Heap is the manual memory allocation. It is used to perform manual memory allocation when you are assigning any sort of variables or data points for a particular application. Any manual memory allocation is done through the heap. A very common way of identifying heap is if you see instructions or instructions like malloc or calloc being used in the code. This is a very good indicator of heap being used. Another place where the heap is used are when you declare global variables or static variables. In these scenarios also the heap is used. The inner workings of the heap are a little is quite complicated. That would require a separate talk on its own. But for now, what we need to understand from the heap is it is manual memory allocation. It is used for that. And when you see commands like malloc and calloc, it is a sure thing that the heap is being used, or in instances where you have global or static variables. Any questions on heap? Okay. The next component after the heap are registers. We briefly discussed registers as well in the previous slides. Registers are storage areas in the processor. The processor needs to store any particular value during its operation. It uses a register. There are two broad specifications for registers. There is a set of general purpose registers and there are reserved registers. These have separate functions and are used in separate places in assembly. We will see the general purpose registers more when we go to the future slides where they are used. For now, we are going to concentrate on the 3 reserved registers that you can see on the screen. The first one is EBP. What this stands for is base pointer. The EBP or the base pointer points to the top of the stack. I will talk about stack a little more in detail in the following slides. But for now, all you have to know is that a base pointer points to the base of the stack. The second reserved register is a stack pointer, ESP. This, as the name suggests, represents the top of the stack. So you have EBP, which is at the bottom of the stack, and you have ESP, which is the stack pointer, which is at the top of the stack. The third reserved register that we are going to look at is the EIP, which is the instruction pointer. As the name suggests, this the instruction pointer points to the memory location of the next instruction that needs to be executed. So if you are doing any debug analysis or you are attaching breakpoints to an existing process to see what is going wrong, if you want to know what is the next instruction that is going to be executed, you don't know where you are in the application, it is always a good idea to look at the instruction pointer, because that will tell you exactly where the flow of execution is going to be next. Any questions? So now I mentioned stack in the previous slide. Now so the third component, the obvious component is the stack. The stack is a very important component in the binary. What is a stack? A stack is a data structure composed of elements. They hold certain data, they have elements, and each element is referenced with the address. And you use that address to reference to either remove or add it to the stack, or if you want to use that data in some way, you have a reference address on the stack. The way to handle instructions on the stack is by a push or a pop. These are the only two instructions that can be used on the stack. The push instruction, if you can look at the picture on the right, pushes an item to the top of the stack. So if I were to push a variable onto the stack, the existing stack is like this. It will push this item to the top of the stack, and the stack pointer, which was pointing to this block, will now point to the highest, will now point to the top of the stack. So it will move up by one location in memory. Similarly, pop does the exact opposite. It removes the last element from the stack. So if you are going to pop the last value of a stack, it will remove that element, and then the base pointer will move down one location, one memory location. Apart from these two, apart from push and pop, another very important thing to know about how the stack works is addresses the lower elements of the address. So because you can only add one thing at a time and pop one element at a time, the stack is structured in first in and last out format. So what goes in first can only be removed after all the other elements have been removed on top of it. We cannot randomly access any other point on the stack other than the top of the stack. And the addresses increase as they go down. So that means if the last block here on the stack is, for example, a memory address, say 100, this is going to be 99, this is going to be 98, 97. So they move, the higher the element on the stack table, the lower the address is. This can be a little confusing if we are seeing this for the first time, but familiarizing yourself with how the stack works is a very important concept to be able to reverse engineer applications in real time. I hope this was clear. If I need to repeat again how the stack works, I can do that. Okay. Moving on, then the final component of a binary are its instructions. So commands to the processor, the instruction set for each architecture is predefined. So if you have a ARM architecture, there is a separate set of instructions. If you have a 64-bit architecture processor, there is a separate set of instructions. So the instruction sets are predetermined. So knowing which processor you are working with is going to determine how the effectiveness of your reverse engineering. The components of the instructions are very straightforward. You have an operation and you have its arguments or its operand. The number of arguments vary based on the operation. I have added one instruction here as an example. The move instruction, the command here is move arg1, arg2. So this has one operation and two arguments. What this does is it moves the contents of arg2 to arg1. This is just an example of what an instruction looks like. So to summarize, we have four components of an executable. We have the heap, which allocates manual memory. We have registers that store values for the processor. We have the stack, which is a structure of data elements. Another thing I forgot to mention on the stack is when a function is called, every function has its own separate stack frame. So when a new function is called in an application, a stack frame gets initialized. We will see how that happens in examples forward. But for now, when a new function is called, there is a stack frame that gets created for it. And when we return back from, or when we exit from that function, the stack frame gets destroyed. And all the values in the stack frame are considered as data. Everything outside of it is considered junk for that particular instruction. So if you have, so you might have a question here. The first time I read it, I had a question myself, was if all the variables and arguments outside the stack frame are considered junk, then how do applications or how do processors work with global variables, where the variables are declared outside the stack or outside the function? So it would be considered junk for that stack frame. Can anybody take a guess on how that would work? What would happen in terms of global variables? If any of you thought of registers, that is the correct answer. So you cannot move memory from one point in the stack to another. You have to use registers. So when we have global variables, even though everything outside the function's stack frame is considered junk, the registers will bring in the global variables if they are needed to be used in that particular function, because those are the memory storage components of the processor. Any questions so far on the basics that we have covered on the okay? If there are no questions, then we will move forward. So I think we have done a lot of theory. We have defined a lot of things. Finally, it is time to actually look at some assembly code, maybe, and try to do some reversing ourselves. So just to recap what assembly is, it is language that is designed to translate instructions that are executed by our computer. The actual code that is being run in our systems, that is translated into human readable format. So we will take a look at how that can be different from actual code that all of us are familiar with, that we write or read about every day. How assembly code is different from that, we will take a look at it with this example. So here I have a sample C code. It is a very basic function. There is an stdio that is included. There is a main function that is declared, and in the main function there is a puts for a string. It will print that string out. So when we compile this application using a compiler, I hope you guys remember compiler. When we compile this application using a compiler and then reverse or disassemble the main function after it is compiled, we get something like this. It looks a little different. It can be a little scary at first, but with enough familiarity, even you will be able to make sense of this. So this, what we are looking at is the equivalent assembly code of the higher level C code that we saw in this slide. Now let us see how is it performing the same function and how is it performing. Before we do that, let me just take a moment to explain all the things that you are seeing here in the assembly, in the disassembled format. The top left, the first thing you will see here is the address of main. So main is located at 1135. This is the memory address. You can see the first instruction, and in the following instructions, it goes down to subsequent memory addresses. So this is the location in memory where this code is sitting, the column on the left. The instructions is the third column here that we see. We saw the move instruction before. There are a lot of other instructions which are defined in the instruction set, and those are used, the compiler uses them as and when an operation needs to be performed. So these are the instructions and these are the arguments. Now this in between are the opcodes. So the machine does not map words or instructions like we do with letters. They have opcodes for it. So they run that particular opcode. When it sees that opcode, it knows what to execute or what is the next stage. So this is the opcodes in the second column. So you have the addresses, the opcodes, the instructions, and finally the arguments. Now let us take a look at what this code is actually doing. So the first one is push RBP. It pushes the base pointer. So push, if you remember, comes from the stack. It is when you want to add something to the stack, you use the push instruction. The RBP is a general purpose register. No, it is a reserved register, which is the base pointer. So push RBP pushes the current value of the base pointer onto the top of the stack. The next instruction is move RBP, RSP. So move also we have seen earlier, it moves the value of the second argument into the first argument. So what is this doing here is the stack pointer, the contents of the stack pointer, which is the top of the stack, are now moved to the base pointer. These two functions together, okay, what they are trying to do is they are initializing the stack. So when a new function is called, in this instance main is called, the previous function that called main has a stack frame of its own. So it is pushing the base pointer of that to the stack, and then it is moving the stack pointer to the base pointer. I hope that made sense. I can show a visual representation of what is happening in one of the previous slides. So here we have the function. There is a stack pointer on top and there is a base pointer in the bottom. So when we do push RBP, the base pointer gets pushed to the stack. It comes here. The next instruction is move EBP, ESP. So the contents of the stack pointer now go to the base pointer. And so this stack frame is discarded. And because the base pointer has now moved, a new stack frame has been created for the new function that has been called. All right. Hope that was clear. The next instruction that we are seeing is LEA RDI in square brackets RIP plus 0xEC4. LEA stands for load effective address. So this is part of the instruction set. So we use LEA when we need memory address calculations. That means we want to do some computing with memory, but we don't want to actually affect the memory address. That means the values at the memory address, we don't want to make any changes there, but we just want to do some calculations. We use LEA. So this function, this instruction, what it is doing is RIP is the instruction pointer, which is going to point to the next instruction that is going to be executed. RIP is added with this value. So the addition of these two is going to give us a new address. And that address, so when anything is put into square brackets like this, it is a reference. It is not taking the actual value from it, but it is referencing what this value is representing, and it is fetching that value from memory. I hope that was clear. And once the referencing is done, it is then loading that effective address into RDI. RDI is a general purpose register, which we briefly spoke about in registers. There are a lot of them. So as and when we come across general purpose registers, we'll see them. RDI is one such register. It is called the destination index. The next instruction. So here RDI is being loaded with some data that is being fetched from the memory location of the addition of these two values. So that is what the third instruction is doing. After the stack has been initialized, the processor is going to this position, this point in memory, and it is fetching fetching the value from there, and it is loading that value into the RDI register. Now we have a very interesting instruction, the next one. If you look at the next instruction here, it says call 1030 and it has a puts at PLT. Now we have used puts in our code here, but we have not defined it anywhere, right? So then how does the processor know what to do when it sees puts? It knows what to do because we have included the stdio.h. So puts is defined in that. So it knows, it is referencing the definition from stdio, and then it is executing what the puts function is supposed to do. But on the machine level, when you look at the assembly code, we see a PLT at the puts. PLT stands for procedure linkage table. It is primarily used for loading modules, loading definitions from other modules. So whenever you see an instruction with PLT in it, the first thing that should come to our minds is the definition for this is not in the code I am analyzing. The definition is coming from some other module. The procedure linkage table is fetching that definition so I can execute the function here. To summarize these four instructions on what they are doing. So the first two have initialized the stack. The third instruction is bringing some data from a particular memory location and loading it into RDI. And the fourth instruction is calling the puts. So when puts is called, it checks the content. The actual definition is it checks the content of RDI and it prints that content out. So by loading our string value, which is hello world, which can be found in this memory location, instruction pointer plus 0xEC4, by loading that value into RDI and then calling puts, it is essentially printing the string that we had written in C. So as you can see, the assembly at a first glance, it may not seem like it is doing the same thing, but when you actually understand the individual instructions, you understand that it is performing the same action, but this is the procedure in which the processor is performing it. So this is what is actually being executed on your system when you run that code. The last three instructions that followed after the puts is a no. This is a no operation instruction, so it does not do any operation when it sees a NOP instruction. The register values remain the same, the flag values remain the same. Basically, what this does, sorry, basically what this does is it creates a delay. So if we write a delay into our code, sometimes because we want to see better results, or there is some time that we need to wait, all of those delays that are generated are done using the NOP instruction. The next instruction is pop RBP. If you see, when we entered the function, we had pushed and the base pointer value onto the stack. And now when the instruction has finished execution, it is now popping the value back out, so that, and then the return instruction, which is the last instruction, sends the instruction pointer back to the function that called the main function. So we have the first four instructions, which are initializing the stack, performing the puts operation. Then there is a NOP instruction. And then the last two instructions are cleaning up the stack frame, because the function is done. We are exiting the function, the main function. So the pop is going to remove the stack frame and revert back to the older stack frame, which was in use before the push came in. And the return sends the execution command back to the function that called it. I will leave it here for a moment. Just go through this. If there is any questions at this point, please let me know. All right. If I hope this was clear. Now that we have seen an actual how C or high level program is converted at the assembly level, uh, the next thing that we are going to do is let us reverse our first binary together. I'm going to move to the lab. Gaurav, if there is anything, just let me know. I can't. Okay, I can actually see it here. Never mind. Is my screen visible?
Abhinav, there are two questions.
Okay.
One is EPI, is it instruction pointer? And
Sorry.
the
Can you
second thing
repeat
is
that?
by, yeah, EPI, EIP, is it instruction pointer? And the second thing is by manually allocating memory, you mean allocation at runtime, right?
Yes. For the heap, manual memory allocation, it can be at runtime. Sometimes it could be even dynamic memory. That means you don't know if you are, let's say there is some user input text field that you have uh, programmed in your code. Now you don't know if the user might enter 10 or 20 characters. It is left to the user. So when you're unsure about how much space is needed, that type of manual memory allocation happens through the heap. And you said EIP, Gaurav, the second question?
Yes, it was around EIP. So EIP, the person is asking, is it instruction pointer?
Yes, EIP is the instruction pointer. RIP is also the instruction pointer. The difference is in 32-bit, it is represented as EIP, as you can, where is it here? Sorry. It is represented like this. When you are doing it in 64-bit, it is represented as RIP. It is the same thing even with base pointer or with stack pointer. When you are referencing it, the R or the E is the how much of space you're actually how much space in the register you are taking based on the architecture. That is what is the difference. But IP is the instruction pointer. Was that it?
Yeah, these were the two questions currently. Yeah.
Okay. I hope I'm not going too fast. If I need to slow down, please let me know. I have a lot to cover, so I might tend to rush. Okay. If there is no more, now we have seen how this works in theory. Now let us see what we can do in a binary. So I have a lab here for you guys. I hope my screen is visible. So here you can see lab one, we are going to be taking a look at an executable file. So we have lab one here. What I will do first is I will run file on it to see what type of file it is. As we can see, it is a Mac O 64-bit executable. So this is a Mac binary and it is 64-bit. So since it is an executable, the first thing I will try to do is I will try to execute it. So when I execute it, I get a usage key. So let me try to put a key in here. You can say key 1, 2, 3, 4. Oh, my bad. Lab 1. And no, so it is still giving me, it is not giving me anything else. It is just asking me to use the binary correctly. Now we will get into reversing this a little bit, see what is happening. Now to reverse this, I'm going to use Radar. Radar is an open source reverse engineering framework. You can use it to reverse any type of binary. It is very versatile. It has a slight bit of learning curve, but once you get familiar with Radar, it can be a very useful tool in reverse engineering. So I'm going to use the command R2, which is Radar, and then I'm going to run the binary. So in here, as we can see, once we are inside, what do? We have no idea. So if I want to analyze, I know there is an A, but the best thing to do would be to one second. Not sure what happened there. Please give me a second. Okay. Yeah, this is where we were. So here, as you can see, so we were in the, so here I'm going to first run the help command to see what options Radar has. There is a lot of them. Most of them are for more complex analysis. For general analysis, you will not need so many. One interesting thing that I can see is the -A option. So what it says is it will run AAA command to analyze all the reference code. So it will analyze the code, which is what we want to understand how this binary works. So we're going to go into Radar once again and do AAA. Now the analysis is done. It has also auto-named some functions for us. Now I want to list the functions. So I can use AFL. So now this is going to give me the list of all the functions it has analyzed and auto-named. So there is an entry function, which is usually is a good starting point. So to print the disassembled, there are many instructions. What I like to use is PDF at entry 0. If you want to print any other instruction, also you can just do PDF at that particular function. And as you can see here, we have some assembly code, which it looks kind of similar to what we have seen so far, not that different, but Radar also does a bit of coloring so that it is easier for us to read. Apart from that, it also leaves some helpful comments wherever it seems necessary or wherever it can figure out what the particular instruction is doing. So that is also a little helpful. Okay. Now that we have taken the main function, let us see what is happening. So first instruction, push RBP. Second instruction is move RBP RSP. I hope everybody is familiar with these two by now. This is initializing the stack frame for when this function is being called. Now there is an interesting function that comes afterwards, which we have not come across, which is subtract RSP 0x10. What is this function doing? Is this part of the initializing or is it part of the code? Does anybody want to take a guess? I'll see the chat in case somebody would be. Okay, no guesses. Okay, this is part of the initializing stack frame. Why we did not see this in the earlier instruction was because if you look at this function, there are no variables, there are no arguments that are being passed. So the stack frame, even though it initialized the stack frame from us, because there was no data to be stored in it, it did not allocate space by moving RSP down. Whereas in this function, where what we are seeing right now, we have 3 variables and 2 arguments. What they are, we have to still see, but we are going to, but because there are variables and arguments, after pushing the previous stack frame, the base pointer to the stack, and it initialized the new stack frame, and it also allocated space to put these variables and arguments into the stack. So that is why there is this extra line that we are seeing here that wasn't there in the previous example that we saw. Okay, now this is initializing. Initializing is done in the first 3. Let us go to the next command. Now here, the next 3 instructions are telling us that the variables, the stack frame that was just created is adding the argument, the variables are being added onto that stack frame. So you have 0 that is going into 4h var underscore 4h, which is our first variable. Then you have EDI, which is a general purpose register, which is going into 8h, and RSI, which is our second argument, is going into 10h. Now, after the variables have been initialized, what is happening next? You can see there is a compare d word to var 8h comma 2. So it is checking if the number of arguments, because var, the first one is 8h and then it is 10h. So these are the subsequent locations in the stack. It is one after the other. Both of these, it is comparing 8h with 2. So what that means is, and what happens after this compare, if it is not equal, that means if the number of arguments is not equal to 2, so the next instruction, which is jump if not equal, so we give any more or we give lesser than 2 arguments, you can follow the line here. Radar actually helps you follow through jumps very easily. So I'm just going to do it. As you can see, the line goes all the way down here and it jumps down here to 1003 EE9. So if we don't give 2 arguments to the processor, it is going to move to this and it is going to tell us usage key. I'm just going to, yeah. So if we look at the lab one, and when we do key 1, 2, so if we enter any other number of arguments other than 2, which is, so here there are 3. One is the file name, which is argument 1, then we have a key, and then it is 1, 2, 3, 4. So because there is more than 2 arguments, the compare is failing. It is jumping to this part of the instruction where it is saying the usage is not correct. So to use it correctly, we need to have 1 argument and the second is the key. So as you can see now, we did not get the same output as last time. We have got a new result, which is checking license 1, 2, 3, 4 and then wrong. So now we have figured out the correct way to implement this and looking at the code. Now let us go to the next. We are still getting a wrong license. So is there something more we can do? So if there are 2 arguments provided here, the jump instruction will be equal. So it will not take this jump. Instead, it will move to the next instruction. The next three instructions that we can see, it is moving the second argument, which is the key we are providing, which is in 10H, that is moving to RAX. Then RSI is getting RAX plus 8. And then this string is loading, which is check license. So that is the next line that we are seeing, which is printed here. It says checking license, and then it prints the license we have entered. Okay, so far so good. And the next two lines are calling the printf statement to then print that value here. Let us see what is happening next after this. Now, the next two lines, the next two instructions that we see here is taking the license key we have provided, and then it is taking 8 bits more from that point, and it is loading a string into RSI. It is taking RDI. These two, RAX is also a general purpose register. We have found one more general purpose register here. So RAX has the variable, then RDI is loaded with character S1. We can see a comment here. The second the LEA that comes after it already has a predefined string, which it is bringing in from memory. So when you actually go and see what is happening in the next line, it is doing a string compare. So the license we have entered is being compared with this string in memory. And if the compare is equal, EAX is 0, it is going to jump, saying if it is not equal, it is going to jump to 1003 ED6, which gives us the wrong value, which is the next string that we see. But instead, if the compare, the only way the compare is going to be equal is if we also enter this licensing key. So that's what we are going to try and do here now. We are going to take lab1 and A Z10N42. Okay. And there you can see we were able to not only understand how the particular binary works without looking at the source code, but we were also able to figure out how to bypass the licensing check that it had by analyzing the source code. Any questions here? Is this main function argument? I see one question. Yes, Vinit Nair, wouldn't it be? Yes, this would be the correct implementation. As we can see, if we enter more than one argument, it fails as the code shows us. I'm not sure what the second question is. If you can maybe reframe it. I didn't get the second question. How do you close this? Any other questions apart from this in how we analyzed this binary to make sense of the code? All right. If there is nothing else, then we will move on. Okay, so this was a standalone library where we had the answer hard coded here. But in real world, these are not scenarios that you would come across very often. You will not have the license or the encryption that you need to bypass just hard coded in the application. Usually now in the real world, you very rarely see applications like this. So the next lab, we will try to go a little more into real world scenario where we are going to, I have an APK here. Let me just clear my screen. All right. and I'm going to print the next. So here I have an APK. This is a little more closer to real world. Now let us see, is there anything we can figure out by analyzing this APK, and is there any uh, potential attack that we can do? Is there a security vulnerability here? Let's take a look at it. So since it is an APK, the first thing I'm going to do is I'm going to run JADX on it. JADX is a open source tool again, which converts Dalvik and Smalley code to human readable Java code. This is also open sourced, so we can let me run JADX and let us analyze what we see from here. Okay. So first thing we have is the name of the application. Now, entering into it, I see there is a main activity and an R class, but pretty much that is it. There is no other code. Now, to see if this application actually works, let me install it on my phone and see what is going on. Here, I'm going to okay, so here I have a very basic application. It does run. So what this does is it is a string encrypt function. This is a very basic function. So you enter any string here and you press encrypt, it will encrypt it. This is part of a bigger application. I have just taken this part out, so you can't see the result here. But when we reverse it, you will see what is actually happening, and you will actually see a little bit of the encryption. So we have first we can confirm that this is not a native app because there is no Java code present anywhere here. I think the first hint that we should get on Flutter is there is a io.flutter here. So this could be a Flutter application. The best way to confirm Flutter apps would be to go into the library, and if you see the Flutter binaries for each different architecture, so for ARM64, for x86, you have a libapp and a libflutter. So this confirms to us that this is a Flutter application. So when Flutter compiles an Android app, it creates these two binaries for us, the libapp.so and the libflutter.so. From a reversing standpoint, libapp is the interesting file because all the Dart code that we write during development of the app, all of that is stored in libapp.so. libflutter packs the engine at runtime. So it has more of the Flutter framework is in the libflutter.so, and the libapp file has the code that we have written. So I'm going to see if I can do something with the libapp file. Now, since this is not a native app, there are some special tools for frameworks like Flutter, which can help us in analyzing and reversing Flutter applications. One such tool that I have used here is Doldrums. Doldrums is an open source tool again. It is primarily used as a parser and an extractor from Flutter binaries. I have already ran the tool to make it a little easier, and I will show you what it means. And we will just quickly go through this to see what we can do with a tool like this when we are reversing a Flutter app. So this is the output of Doldrums. As you can see, there are a lot of general data about the binary. what type of conversion, what type of compilation it did, the version number, all of this. We are not really interested in all of this. So the main thing that Doldrums does is it identifies the functions that are written in Flutter, which are in the memory location, and it gives us the offset of those functions. So if libapp.so is sitting at 100,000 or 1 lakh memory location, for example, this particular class that you see can be found at this offset. So if you add 1CB4EC to the base value, which we have assumed is 100,000, if we add and reach that memory location, we basically have this function's stack frame, we have this function's arguments. This function has been initialized at that position. So that is basically what Flutter does for us. When we are working with native applications, we need the offset values of the functions to be able to analyze them, to be able to find them in the binary and then analyze them. Now, you might ask, what can we do with this offset value? Is this even useful? It just looks like data to me. Let us look at what we can do with this. Now, since this is an encryption function, I'm going to make an educated guess that there might be one function with the word encrypt in it. So since it is a very big file, I'm not going to manually go through it right now. We will speed things up and I will search for encrypt. So I'm specifically looking for classes which have the word encrypt in hopes that I can see if I can find the encryption function here. So first one we get is from the wrapper class. So this doesn't look like it. This is encrypted size, not really what we want. Let's go to the next one. Okay. Now we have found something interesting here. There is a home page. So the home page, there are these classes that are being called. There is a generate key class. There is an encrypt class, both of which are being called when from the home page. Now there is one more left. This looks interesting. We can explore this, but let's see if there is an easier one that we can find. The next encrypt that we see is from a class called platform string crypter. This does not sound like any internal Flutter class name. So it probably is a module or a library that has been written for encryption. We can confirm this. Let's take this and let's head over to Google. Let's see what Google says. If I Google this and I do get a platform string crypter class here. So this is the library used for encryption. So this looks like a very interesting function, a very interesting class. And in this, encrypt is being called. So let us see if they have any information on the encrypt method. As you can see in methods, encrypt is used in platform string crypter, and it takes one string and one key. So it has two arguments, which is the string that needs to be encrypted and the key, which is the encryption key that it is going to be using. Now, I have this information with me. What can I do with this? What can you reverse here? I have written a small script, which the script is very straightforward. What this does essentially is, if you give it a function if you give it a function address, it is going to hook into that function and print all its arguments and all its return values. Pretty straightforward, pretty simple at this point. So we have a function. If you provide it with any address, if there is a function at that address, it will print its arguments and its return value. So now we have written this, and we know that encrypt at platform string crypter uses two arguments. One is the string and one is the key. So can I hook into this and see if I can get the encryption key here. We can try that. So what we will do, we will go back to terminal. Okay. And we will start my FIDA server. I have copy pasted my output from Doldrums, which gave me the encrypt, the offset value of this encrypt, and I have added it to this function here, which is finding the base address of libapp, which is what we need first, and then it is adding that offset address to that libapp, and that is where I am hooking. So this is what we use Doldrums for, to get this offset value. If we were to manually do this, we would have to analyze millions of lines of binary code, which can take us a lot of time. So we have open source tools like this, which can help you in reverse engineering, which can make your work a little easier. So I have added this. I am going to start my script now. Okay. And let me, I have added the C. I will save this file now with the new address of the function where I think I can find some interesting data. Now let's come back to the app. Let us enter a string. I'm going to enter my name so we can identify it easily. I'm going to say Abhinav and I'm going to say encrypt. What just happened here? Are you able to see this? I hope all of you can see this. So our script went to that memory location. We understood where the function was residing. We understood what parameters the function, what arguments that function uses. And using that, we wrote a small script to print the arguments of that function. So are these the arguments of the function? We can confirm it quickly. If we look at the third argument that the script is showing, it actually has my name. So if this argument is here, logically the encrypt function's other argument should be this, which is the encryption key. We can try it once more just to be sure. We'll enter a different name, see if it still works. We will say reverse engineering, no spaces. All right. And now we will run this and we can see once again, we got one argument, which was the text we entered, and the second argument of that function, which was the encryption key. So we were able to use reverse engineering, some of the things that we discussed in the slides, to actually obtain the encryption key to a encrypted module in a Flutter application. So similar to this, there are a lot of real world examples. I just try to show you guys a simple one to see what can be done with reverse engineering. There are a lot more examples similar to this. Any questions at this point? I think this is.
Abhinav, there is one question which the person has asked from the previous lab. Does the sim.imp string function has the instruction to store the compare result in EAX?
All right, let's go back to the second lab. 1 second. It's not here. Oh, it's in the other one. Yes. Let me look at the question again. Does the string IMP string compare function has the instruction to store the compare result in EAX? String compare. Yes, string compare stores so EAX is a general purpose register, like I mentioned, and any operations, most operations, the end result is usually stored in EAX, unless it is a default process that most processors follow, unless it is being explicitly used by some other function at that or some other instruction at that time. You can find most of the end results in EAX register. So that is why the result of string compare gets stored into EAX, and then it is being compared with 0 to see if it is actually equal. That's a good question.
There's one more question, for Doldrums. I'll just paste it out for you. Huh?
I can see it. Yeah, I got it. Doldrums and Flutter updating their package. So what would you? Yeah. So if such tools are not compatible, you will have to do it the hard way then, where you will have to analyze, understand how Dart's VM isolate works, and how the classes and this thing is done. You can use tools like Gidra maybe, where it will give you a pictorial representation of the entire binary. So then you would have to do them manually. You can also use radar with some scripting capabilities. If you are able to script and then you can minimize your work with radar. But it is not impossible in these situations. It is a little bit more difficult. So what will take you 5 minutes output from Doldrums and uh, other parsing tools might take you a few hours depending on how good you are with reverse engineering. But it can be done in the same way. Some libraries like AES encrypt and the one you showed, right? Yes, it can give. I have not tried RO data for this instance, but it should be able to give it to you. I don't see why it cannot. In case of static keys, this is not a static key. The Flutter application it uses a dynamic key. So each time the function is called, the key changes. So there is not a lot of luck. If you actually look at the keys, they are changing. Have they changed? Yes. So they are actually different keys. I just confirmed it just to be sure. But these are not static keys, so I'm not sure how much RO data would be able to give you there. Okay. All right. And we are at the final slide now. So as you guys can see, reverse engineering has a lot of different use cases. There is a lot of different ways to do it. There are some tools that can help you, but it is definitely something that every security researcher should be familiar with and should have in their arsenal. We at Appknox also, apart from the tools that I mentioned here, there are a lot of other tools which I couldn't cover in this webinar. We use an extensive set of tools for reverse engineering when we do our VAPTs to make sure that we are finding all the vulnerabilities in a particular application. And we have ourselves and myself individually, I have found a lot of creative bugs in reverse when I reverse engineered a binary, which would have otherwise not been possible. So this is something I think everybody should take up, especially if you are in the security domain. And this was hopefully this webinar gets you interested in reverse engineering and you were able to learn something from it. And with that, I will conclude. If there are any more questions, I can take one last question maybe. If there is nothing, we can wrap up. And I did overshoot by 15 minutes. Sorry for that.
Thanks, Abhinav. I guess there is no question right now. We can wrap up. Thank you, everyone. We'll share the recording via email, and we'll also add it on our website. So you will be able to download it, and also it will be available on YouTube by Monday. Cool. Thank you. Thank you, Abhinav.
Thanks everyone for attending. See you guys. Thanks, Gaurav, for coordinating.